Welcome back to the 8th installment of my series on Earth's extinction events. Today we're diving into one of the most iconic chapters in our planet's history, the Cretaceous, home to the cataclysm that marked the end of the age of the dinosaurs. While this period includes the most famous mass extinction of all time, it also saw several smaller extinction events along the way. These earlier ones may not have been as dramatic, but they still played a crucial role in shaping the path of evolution. If you're new to this series, don't worry, this video stands on its own, but if you're curious about earlier mass extinctions, check out the full playlist. If you'd like to dig deeper, I've linked a document in the description with all the sources and image credits used in this episode. Let's set the scene before we talk extinctions. The Cretaceous period lasted from 143 to 66 million years ago, making it the longest and final period of the Mesozoic era, spanning roughly 77 million years. By this time, the once unified supercontinent of Pangaea had largely broken apart. Though still grouped into two major landmasses, they were drifting ever further apart. Laurasia in the north consisted of North America, Europe and Asia, while Gondwana in the south included South America, Africa, India, Antarctica, Australia and New Zealand. These continents were separated by the vast Tethys Ocean, though many shallow seas still connected them. As the period progressed into the late Cretaceous, this two-supercontinent model became increasingly outdated. The modern continents were starting to take shape, but with some notable differences. India was drifting alone across the Indian Ocean, Australia was still connected to Antarctica, and North America was split into two landmasses by the Western Interior Seaway. The climate throughout the Cretaceous saw some dramatic shifts. A cooling trend that began at the end of the Jurassic continued into the early Cretaceous. Snow was common at high latitudes, and the tropics were wetter than they had been during the Triassic or Jurassic. However, this cooling didn't last. By the end of the first age of the Cretaceous, global temperatures began to climb, likely due to increased volcanic activity. This warming phase brought monsoonal weather patterns to much of Gondwana. Around 118 million years ago, the Earth entered another cold spell that would last through the rest of the Cretaceous. All of these major climate shifts took place during the early Cretaceous. The transition to the late Cretaceous occurred around 100 million years ago, meaning that this cooler, drier phase dominated most of the period. But while the shifting continents and fluctuating climate are fascinating, what really defines the Cretaceous in most people's mind is its incredible biodiversity, and for good reason. This period saw the Cretaceous terrestrial revolution, a major evolutionary event sparked by the rise of flowering plants or angiosperms. Today, these plants make up about 90% of all plant species, but it was during the Cretaceous that they first emerged. Their arrival sent shockwaves through ecosystems. Pollinating insects rapidly diversified, as did vertebrates that fed on fruit and nectar. This explosion of insect diversity, in turn, supported the rise of many insect-eating species, including birds, mammals, and even web-spinning spiders. Of course, no discussion of the Cretaceous would be complete without the dinosaurs. Although stegosaurs disappeared early in the period, many new herbivore groups rose to prominence. Ceratopsians, hadrosaurs, ankylosaurs, and pachycephalosaurs, among others. Sauropods were less diverse than they had been during the Jurassic, but titanosaurs remained hugely successful. Theropods also diversified. Older Jurassic forms gave way to newer, more derived groups like tyrannosaurs, dromaeosaurs, and ornithomimosaurs. In the skies, two lineages of flying vertebrates dominated. The pterosaurs were the largest flying animals to ever live. There's debate on which was the biggest. Quetzalcoatlus is a strong contender, though others, like the bulkier Hatzegopteryx, are sometimes put forward. Either way, these giants boasted wingspans of 10 to 12 meters, or 33 to 39 feet. However, pterosaurs no longer ruled the skies alone. Birds, which had first appeared during the Jurassic, were rapidly diversifying. Some still had teeth and claws, while others looked more like the birds we know today. In the oceans, marine reptiles continued to thrive. At least some of them did. Ichthyosaurs disappeared by the mid-Cretaceous, but plesiosaurs flourished, and mosasaurs made their first appearance later in the period. Reptiles weren't the only marine predators. Sharks, rays, and teleost fish, which make up 96% of all modern fish, were also abundant. Invertebrates were essential parts of marine ecosystems. Straight-shelled ammonites, like baculites, were widespread. Reefs were increasingly built by rudists, a group of box-shaped bivalves, rather than corals. Predatory gastropods became common, with adaptations for drilling into the shells of their prey. Echinoderms like sea urchins and starfish thrived, as did crustaceans like ostracods. The Cretaceous was a turning point in the history of life, an age where many modern groups first emerged or came into their own, flowering plants, birds, and sharks, just to name a few. Yet many ancient lineages, like dinosaurs, pterosaurs, and ammonites, still ruled the land, sky, and sea. By the end of the period, fate would decide which of these groups would survive into the modern world, and which would remain as relics of prehistory. Now that we understand a little about life during the Cretaceous, let's turn to the first of the extinction events, the Mid-Aptian biotic crisis. Surprisingly little is known about this event, despite its importance in shaping the late Cretaceous. As the name suggests, it occurred during the Aptian age, around 120 to 115 million years ago. Several major events were unfolding during this time, most notably volcanic activity in the Ontong-Java Plateau. This region, one of Earth's largest igneous provinces, triggered widespread oceanic anoxia and contributed to global warming. This lack of oxygen in the oceans is evidenced by the widespread deposits of black shale, a type of rock that only forms in anoxic conditions. These widespread deposits help researchers piece together the environmental stress of this period. Acidification of the oceans likely accompanied this anoxia, another common consequence of volcanic activity. Global temperatures rose by about 4 to 6 degrees Celsius, likely causing sea level fluctuations as glacial ice melted. Together, these overlapping stresses wreaked havoc on marine ecosystems. If that wasn't enough, you might recall that I mentioned a cold snap around 118 million years ago. It happened right in the middle of this crisis, adding yet another stressor for life at this time. Organisms coping with warming conditions suddenly had to endure a dramatic drop in temperatures. The prevailing theory for this cold snap is the release of sulfate aerosols. While volcanoes emit greenhouse gases like carbon dioxide, which likely drove the long-term warming, they also release sulfur dioxide and other aerosols that reflect sunlight and temporarily cool the planet. The cooling was intense but short-lived, likely lasting just 1 to 3 years. As you might expect, the crisis hit the oceans hardest. The fossil record from this time is patchy, but several patterns have emerged. Planktonic foraminifera, single-celled marine organisms, experienced a dramatic turnover during the Aptian. Their numbers declined sharply, and surviving species were smaller with altered shell structures. Other plankton groups, such as Calcareous nanoplankton, were also heavily affected. Larger marine life wasn't spared either. Ammonites underwent significant turnover, with some families suffering sharp declines while others diversified. For instance, the family Ancylosceratidae, known for their loose spirals with non-touching coils, saw an initial decline in diversity, but radiated later in the crisis. Belemnites, less studied relatives of ammonites and modern squid, also suffered a notable decline. Already more common in high latitudes, they became regionally extinct nearer the equator, likely due to anoxia and warming. Marine vertebrates were already in decline from their Jurassic peak, but the Aptian event is considered a nail in the coffin for some. Ichthyosaurs were hit hard, with several genera disappearing entirely. Although others persisted beyond the crisis, they never regained their former abundance. Marine crocodilomorphs had already been on the decline, but the changing conditions likely hastened their demise. Other groups, like plesiosaurs, sharks, and bony fish, experienced only minor shifts in abundance and distribution. On land, it's harder to pin down the specific effects of the Aptian crisis. This was also the period of the Cretaceous terrestrial revolution, with the rise of flowering plants reshaping ecosystems. While the Aptian crisis didn't directly drive this revolution, it likely accelerated it by opening up ecological niches, allowing angiosperms to flourish. The revolution continued long after the crisis ended, so the environmental disruptions played a secondary role. A notable loss during this time was the stegosaurs. The last known genus, Wherosaurus, disappeared during the Aptian. Stegosaurs had already been in decline, and while the Aptian may have been the final blow, the exact cause of their extinction remains unclear. It's possible that both climatic changes and the decline of gymnosperms, which they fed on, contributed to their extinction. Speaking of gymnosperms, they were another group in decline. These trees, conifers, cycads and ginkgos, had been dominant since the Permian. With the rise of flowering plants, they began a slow and regionally variable decline. In areas less suited to angiosperms, gymnosperms continued to thrive, but globally their dominance was fading. That said, they never went completely extinct. Modern pines and firs are descendants of these ancient trees. Let's continue our journey through time and arrive at the next major event, the Cenomanian-Turonian Boundary. This is sometimes less creatively known as Oceanic Anoxic Event 2. If you're wondering what happened to Oceanic Anoxic Event 1, that was the Mid-Aptian biotic crisis we just discussed. While this event shared many similarities with the Aptian crisis, it had its own distinctive features that we'll explore. This event occurred during the late Cretaceous, around 94 million years ago. It was triggered by massive volcanic eruptions in the Caribbean and high Arctic large igneous provinces. These eruptions released enormous amounts of carbon dioxide into the atmosphere, further warming the planet. By this time, there was no ice at the poles, and sea levels reached their highest point in the entire Phanerozoic eon. Once again, oceanic anoxia returned, though this time it affected deeper waters more than the shallows. Eutrophication, or excessive nutrients, also spread throughout marine ecosystems. Equatorial sea surface temperatures soared, reaching an astonishing 35 to 37 degrees Celsius or 95 to 98 Fahrenheit. Ammonites suffered another round of extinctions, and planktonic foraminifera experienced further turnover. Seafloor foraminifera were hit especially hard, with many species wiped out entirely. Some marine reptiles also lost diversity, but they fared better than they had during the Aptian. Deep-sea fish populations, however, suffered significant changes. While the extinction event affected many groups, it also created opportunities. Teleosts thrived. They underwent a major radiation, filling many of the newly vacated ecological niches. Oysters, particularly those suited to low oxygen conditions, adapted well to the altered environment. On land, the Cretaceous terrestrial revolution continued unabated. Unlike the oceans, there was no major extinctions on land during this period. Instead, regional disappearances and ecological shifts occurred, largely driven by evolutionary pressures. Here we come, at last, to the Cretaceous-Palaeogene extinction event, often shortened to the KPG extinction. This event marked the end of the Cretaceous period around 66 million years ago, and it is considered the third most catastrophic mass extinction in Earth's history, wiping out about 75% of all life. Unlike many of the mass extinctions throughout Earth's history, for the KPG extinction, the primary threat didn't come from below the surface, it came from space. That's not to say volcanism didn't contribute, it probably did, but the main trigger was an asteroid. Calling it an asteroid doesn't really give the right idea of the scale. It was 10 to 12 kilometers in diameter, weighing around 1 trillion tons, and was moving at 72 to 90,000 kilometers per hour, or 45 to 56,000 miles per hour. To put that into perspective, imagine something the size of the urban core of Washington, D.C. or Paris, or as tall as Mount Everest, slamming into Earth at 20 times the speed of a bullet. The energy it released is estimated at around 100 million megatons of TNT, roughly 1 billion times more powerful than the bomb dropped in Hiroshima. The asteroid struck what is now the Yucatan Peninsula in Mexico, forming the Chicxulub crater, about 200 kilometers wide and 1 kilometer deep. Within 500 kilometers of the impact, everything was vaporized. Animals, plants, water, even rock. Temperatures soared to thousands of degrees, followed by a shockwave stronger than any nuclear weapon. Virtually nothing survived. In a wider zone of up to 1,500 kilometers away, surface temperatures soared from hundreds to over 1,000 degrees within seconds or minutes. Vegetation ignited. Global wildfires erupted. Most land animals likely died from superheated air or burned in the fires. Aquatic creatures didn't fare much better. While some deep-sea or burrowing species may have escaped the worst, they had to be deep enough to be insulated from the chaos above. The impact also triggered massive earthquakes and tsunamis. The Gulf of Mexico saw waves over 100 meters tall, and ripple effects were felt across oceans around the world. But what about life farther from the blast zone? These organisms escaped the immediate destruction, but not the aftermath. The impact kicked up immense volumes of dust, soot, and sulfate aerosols into the atmosphere, plunging the planet into darkness. For up to 2 months there was total night. After that, light remained severely reduced for years. This impact winter disrupted photosynthesis, causing plants and phytoplankton to die off. With the base of the food chain gone, herbivores soon starved, followed quickly by predators. Starvation wasn't the only threat. The loss of sunlight triggered an abrupt and extreme drop in global temperatures. The warm climate of the Cretaceous gave way to freezing conditions. Temperatures dropped by 10 to 20 degrees Celsius in many places. Higher latitudes may have seen sub-zero conditions, and even the equator experienced snow. The oceans cooled as well, with surface temperatures falling by 5 to 8 degrees Celsius. It took years for light and temperatures to recover. Ironically, in the decades that followed, the Earth may have overheated, as carbon dioxide from global wildfires caused a secondary warming. Additionally, the rocks vaporized in the impact were rich in sulfur. These formed sulfur dioxide gas, which caused acid rain. Nitric acid also formed as the extreme heat split nitrogen and oxygen molecules in the atmosphere, and the resulting acid rain further poisoned soil and freshwater systems. This acidic environment, along with ocean acidification, made survival even harder for life. Around the same time, volcanic eruptions from the Deccan Traps in India released more CO2, contributing to long-term warming and ocean acidification. While volcanism had been happening before the impact, the asteroid likely exacerbated the volcanic activity, adding to the environmental chaos, weakening ecosystems and making the biosphere more vulnerable. Around 75% of all species were wiped out. The non-avian dinosaurs, pterosaurs, and most marine reptiles, except turtles, vanished. Ammonites, belemnites, and the reef-building bivalves disappeared. Many planktonic species, fish, plants, lizards, snakes, and insects were lost. Why? Because many of these species lacked the traits that favored survival. Large body size, sensitivity to cold, reliance on shallow habitats, specialized diets, or dependence on complex food webs all proved fatal. Ammonites and belemnites struggled with acidification and the collapse of plankton. Large surface-feeding fish declined sharply. Up to 90% of lizard and snake species vanished, especially those that were large or had specialized diets. Insects, particularly specialist pollinators, were also hit hard. Plant life collapsed as well. Both angiosperms and gymnosperms were decimated. Forests were destroyed. So, what survived in the post-apocalyptic hellscape? The organisms that made it through often shared a few key traits. They were small, requiring less food. Many were omnivores or detritivores, generalists able to survive on whatever they could find. Some were burrowers or lived deep in the ocean, shielded from surface chaos. Many of the survivors are familiar to us today. Birds were the only dinosaurs to survive, likely due to their small size, flight capabilities, and seed-based diets. Seeds were one of the few abundant food sources after the extinction. Mammals were mostly small, burrowing, and nocturnal. They had diverse diets and were well suited to sheltering underground. Crocodilians survived despite their size. Their ectothermic metabolism meant they needed less food and freshwater habitats were less disrupted. Turtles also fared well. Their hard shells offered protection, and their aquatic generalist lifestyles gave them flexibility. Teleost fish thrived, aided by their adaptability and global distribution. Sharks and rays suffered some losses, but many survived, particularly those in the deep oceans. Amphibians surprisingly did well. Their low energy needs and burrowing or aquatic habits helped them weather the crisis, despite being sensitive to environmental change in most other mass extinctions. And then there were the fungi. Someone left a comment on one of my recent videos asking whether fungi were affected by these extinctions. The answer? Not really. Fungi don't rely on sunlight, and they specialize in breaking down dead material, something there was plenty of after the extinction. Fungal and bacterial blooms followed the collapse of ecosystems. Other early colonizers, like ferns, also flourished in the aftermath, and angiosperms returned to thrive not long afterward. So, there we have it, the most famous extinction in Earth's history. It may not have been the largest, but its impact was arguably the most profound. It reset the evolutionary clock. In the vacuum left by the extinction, the survivors radiated into new forms. Mammals rose to dominance, birds soared into new ecological roles, flowering plants rebounded, and teleost fish spread across the oceans. It was the beginning of a new world. I hope you enjoyed this video. The Cretaceous was a fascinating chapter in Earth's history. Known for its dinosaurs, but shaped by multiple biotic crises, and ending in a cataclysm that reshaped life as we know it today. Next week, we'll return to explore a unique group of animals, featuring an intimidating relative of pelicans. But next in this Extinction series, we'll march into the Cenozoic era and discover what came next for life on Earth. Thanks for watching and, as always, let me know your thoughts in the comments below.